Thanks, everybody. I'm very happy to be here. As you heard already, we will be talking about Bayesian risk optimization. Just a bit about myself. Carlos Trujillo here, working with PyMC Labs. I'm also working at WISE. We are developing open source packages. Nathaniel, it's also part of our group if you were in the previous session. And we will go a bit deep in PyMC Marketing as well, and how can you use it for all of these optimization problems. A bit of the agenda of today, I will give you an introduction of media mix models so you can know what they are. We will also talk about the typical optimization challenges that we tackle every time that we have these models. We will go through what are the benefits of taking risks into our optimization problems, and then by the end of the day, hopefully you will get some recommendations and conclusions. So to kick off, if you're not familiar with Bayesian Media Mix Models, are basically fancy linear regressions. So you want to take a problem, a target variable, whatever that target variable is, can be your revenue or your number of sales, or just, I don't know, app installs or registrations if you're in a startup or similar, or an app. And you want to try to understand what is the value of each of these marketing activities, such as invest in Facebook, invest in TV, invest in whatever type of advertising, and assign a credit to each of those to later on, based on that understanding from the model, optimize your strategies and your resources. So you spend better and you get more money back every time that you spend. If you want to represent that like in math, this will be like a bit of the formula where you have like this function of x, which in this case, x will be your media or your drivers, the ones that you want to decompose and understand. Even when it sounds like a typical linear regression, MMNs have something that makes them special, and it's these three type of specific functions. One of the first of those is the add stock or lagging function, which basically help us to understand how much of the spends of today are lag to tomorrow. So you can not only understand the impact, your immediate impact, you can understand also how much impact is driven in the next subsequent days. And on the other side, you can also understand what is the saturation of every channel. So we understand that we don't have infinite returns. We will spend money until a certain point, and that money will start to saturate. So we'll not generate so much results back. And on top of that, most recent models are adding these varying media effects, which basically means that the parameters of your saturation or your ad stock will change over time. So in the same way that customer behavior change, the estimations of saturation or lagging effects also change. And we want to understand what is the best budget, the best way to spend money, go through these functions, and optimize or maximize the value that goes out of it. So in a nutshell, if you want to understand how this works, you could actually go to PyMC Marketing and see a bit of the under the hood. This talk will not go over it, but in short, you have a set of channels, let's say X1, X2, X3, and X4. You can think about it, again, as advertising in Facebook, Google, television, or any other type of advertising placement. You will build a model in PyMC. It's as simple as you see there. You can use the JAMA configuration file, define your model in a JAMA file, pass your training and your training data. And once it's done, you will get estimations about all of these effects. So in this case, I'm putting this plot here where you can see what is the saturation that we will able to infer over the data in every of our channels. So once you have that, and if you build your model in a robust way, ideally, again, what do we want to understand is what will happen if we intervene in X. So we are not only searching here the probability of Y given the data, we're actually searching the probability of Y given do X, and we want to assign a value to that X. Right now, here you can think about B as the plan that you want to do in order to make this intervention. So I want to spend more money in certain placement, and I want to see what will happen to my outcome. So if we understand this properly, that means that we can start to create these counterfactual scenarios and start to ask this, what if? What will happen if I follow plan A, plan B, plan C, and so on? And once we understand all of them, we could theoretically decide which one is the most beneficial, or which one is the combination that will maximize or minimize whatever function that we want to observe. In a regular day-to-day basis, how that will look like, or the first question that you will ask yourself is, okay, if I spend a certain amount of money in a certain way over these channels, what will be my response? And probably, as in any either Bayesian or frequencies model, you will get an estimate around the mean of that, and that will tell you something like, okay, if you spend $59, you will get something like $200 back. And then you have this basically a scatter plot. And you could, because you understand how much money you're getting back from your investment, you can estimate, let's say, the return of investment over that spend. So in this case, if you take it for this example, it's like 3.98. So basically, we will get a 3x over the spend that we generate right now. And probably this is nice or not. Like, it's up to your company to decide. But in this case, let's say that you are looking for or searching to get ROI of 10. So if you see this, you are like, okay, following my current plan, I don't hit my target. So what we can do? And that's basically what optimization it's made for. We want to, in a nutshell, the problem that we want to solve is to find a set of a vector x that when it's passed through a function will maximize, or in this case, minimize, the value of that function. And then either your function of x or your x can be under certain rules, what we will call constraints, and those constraints will be either equality constraints or inequality constraints. So you can say, okay, I want the sum of the vector to be greater than something or equal to something, or I want the function to be equal or greater than whatever, or lie between certain range. That's basically how you will formally write down the problem. And right now, in PyMC Marketing, we are solving that with something called SLSQP, which basically runs minimize under the hood. Now, if you want to do this, then you can just take PyMC Marketing and naively run this optimization, and what you will see is that, oh, now for the same amount of money, we can get 80% actually more results if I just distribute how I spend my money differently. This is amazing. Probably if you go with this output to some of your stakeholders, they will say, oh, that's great. We found a better, efficient way to spend money and get more returns. And because you are spending more, like the same amount of money, but you're getting more efficiency from it, you need to reorganize your resources. You probably will take and spend, I don't know, more money for your office, or will get, I don't know, new mobiliary or whatever. Like, you will make commitments to spend this extra revenue into something else. And here's where things go tricky, because you make this estimation with your model. Again, your stakeholders are happy, and all of a sudden, you didn't hit that target. Like, oh, I did what the model recommended, but I didn't get the results that the model was saying to me. And that happened because basically the uncertainty around your response eats you alive. Every time in a Bayesian model, every time that we run a set of estimations, we don't get a single point over that estimation. We get a probability distribution over the possible outcomes. And that probability distribution could be either very center around the mean or very flat and wide around the mean. You could have also heavy tails, which in this case, that's exactly what happened. If you actually see the optimized allocation following the recommendation that our algorithm found, have a lot less density around the mean than the initial allocation where our initial plan was positioned. That means that in our first case, we were a lot more certain about the outcome than in our optimization case. And again, no joke that we didn't hit the target in this case. If you actually take the posterior distribution from the allocation, the optimized allocation, and check what are the chances that you hit a value close to the mean, it's actually less than 43%. So again, chances to get that were sort of an outlier. So the question will be, and I just realized this after talk with a friend, if you were in the previous talk, what we can do in order to, like satisfy our CMO, because that's a regular problem in marketing. We want to spend money, get some money back, and we don't want to basically waste anything. So the worst nightmare that someone in your company could, have is like, oh, I spend money in marketing and I just waste it. And the way to do it is, first, we need to understand uncertainty. And once we understand uncertainty, we need to start to apply it to our problems. So in any problem, we have two types of uncertainty. First is aleatoric uncertainty. This is uncertainty that is related to your data and to this aleatoric process that you will never be able to explain, even if you have all the data in the world. And on the other side, you have epistemic uncertainty, which is the uncertainty that comes to the parameters given the data. And that, as you get more data and you collect more information, your model will shrink it, because your model has just more data to explain the parameters. So what you want to do is probably play with the second and try to find regions to spend that are well known by the model. So you don't spend over these scenarios that are unknown or less identifiable. And if you actually see the first example and you're asking, okay, where the first uncertainty come from, you could see, at least in this plot, that it gains because majority of the budget it's put into one of the channels with the higher uncertainty. So if you see X4 in this case, the region where we are spending, which is the red line here, it's have a way greater amount of uncertainty than other channels. And again, you can see that because in this region, we ever spent before. So this is a region where we have ever been spending. In the regions where we spend, you can actually see how the curve have narrower credible intervals. So again, if you take this problem and actually think about it, we are not, like the function of x of our vector is not actually a single value, it's a posterior distribution. And that means that we can play against any statistic of that distribution. So if tomorrow you decide, okay, I basically want to make a calculation that, I don't know, take the quantiles and just calculate the distance between those, and I want to prefer distributions which are narrower, you can also translate that and pass it into PyMC, and he will do it. Or you could take more canonical examples, like conditional value at risk, and say, okay, I want distributions we have lower tails, like not longer, shorter tails. And you can, again, take this formulation and pass it to your model. So you can either decide, okay, I want to create custom functions and optimize against that, or I can take more canonical functions. And what happens if we do that is actually quite interesting, because you could then take a function, whatever that function is, pass your type of risk type, like how adverse are you to have a value that is less certain or more certain, and by consequence get a very different allocation. In this case, we were using a function that we have internal in PyMC, which is called mean tightness score, which basically just allows you to penalize the value of the mean depending on how spread is your distribution. So if you have a distribution which is quite wide, the value of the mean will get penalized higher if you have a more risk-adverse profile. And if you are not so risk-adverse, the opposite will happen. You will prefer mean values that are larger, even if the distribution is wide. In this case, I just select, like, I want to make an optimization very safe. I want to be very sure about the results. And as a consequence, the model decides to then spend over regions where we have a lot of information. You can see that in this case, every red line for the plot, it's in all the spaces where we have a lot of dots, where we have a lot of information. So the model decides now, because we have this new utility function, to spend in regions that he knows. If now you see the response, you go understand that even better. because you can see that the new risk-adjusted response is actually even shorter than the guessed or the optimized ones that we have at the beginning about the results. So we have a lot of more density around the mean. That means that the model is more and more certain that we will get that output. And probably, again, you are already seeing that even when we are very sure about the mean is actually lower. And if you're asking something like, okay, that means that if I want certain responses, I need to just accept lower values, and that's not the case. You could perfectly say the opposite. You could say now to your optimization algorithm, oh no, I'm not so risk adverse. I can tolerate a certain level of risk, and that will now bring you a new allocation which gets you a value which is not as uncertain as ignore risk at all, but it's not as certain as not ignoring risk. So we have now something like until the middle. You could iterate here like basically forever. You could just, again, define your risk value and try to find different optimizations or distributions of your money until you hit something that satisfies you. But something very smart that you could also do is, well, let's encode the goal that I'm searching for and pass it to the function, and let the model tell me, okay, what's my outcome? What should be my outcome if I want to hit that specific target? And that's basically what, again, it's able to, like PyMC Marketing is able to offer you. So you can take custom functions, you can take a heuristic, again, approximation from a risk function where you want to say, okay, I have a target, and I want to find a distribution which have a lot of density around that target. And once you write down this into code, you can pass it to PyMC Marketing, and now we will be minimizing, or in this case, maximizing a posterior distribution that has a lot of density around that specific target. And the result of that is, as you see in the right hand, it's a new distribution that is not quite center, but is more center around the target than all the previous one. And if you want to, let's say, be like really Bayesian and even destinate or define a region of equivalence, what we call rope, you could say, well, I will take the same decision even if my target is plus minus 1. And if my target is in that region, then I'm happy. And here you could say that once you define that region, that you can just make it out of your business sense, how sensitive will be your outcomes if you change something. The probability of the model returning a value in that region is like 58%. So now you basically did an optimization where you consider the risk of the model that came in early from it, and you find out a specific distribution or allocation of money that will give you a more certain outcome. So hopefully you will not be get into the fire where you didn't hit the target and then you spend like a lot of more money than you actually have. So a bit of the recommendations that I want to share today is, if you're doing optimization, if you're taking any model and you want to optimize something, try to not do it blindly. Consider uncertainty. Consider that model will have regions that he didn't explore or he don't know so well, and you need to understand that and take it into account. You need to also understand your risk appetite. Like, if you get this amount of response, what you will do? Like, something will change if you don't get it. You will do something different if you don't get it. Like, all of those type of questions will help you to understand or to discover your risk preferences. And once you have those identified, definitely start to build functions that basically reflect them. So you want to ideally take all of this in consideration once you want to report or get an output. A lot of these things, I don't know, mostly or probably mostly in financial companies happens that marketing is like any other investment. So you can spend in marketing and get some money back, or you can just put the money in a saving account and get for sure a certain amount of money back. So once you want to compare where you put your money, these are very important questions to solve. And I think that's a bit it. If you want to see the full article about all of this, you can scan that QR code. If you want to make questions, you can scan that QR code. In the full article, you will have a lot of more information, but I would love to hear your feedback, and that's basically it. So thank you.
Thank you, Carlos, very much. We also made in time, so we still have questions from the audience. As always, first the online audience, as they are also a bit later, I think 20 seconds. First question from Naman. How much variation do we need in the training data if the spend across major spending channel, example Facebook, is pretty much consistent and has high correlation with dependent variable? Can we still learn from it?
Yeah, definitely. So the problem, if you have a channel that is not varying so much, I would say that that's basically the case when the model will not be able to learn so much from it. So by consequence, the parameter will be quite wide. So you will have a lot of uncertainty there that you will need to play with. And I think that this actually makes very transparent the fact I have a very stable signal, which even when it correlates very well with the target, probably when you see the other variables, it doesn't represent so much response, or is not able to capture any response because, again, it's very flat. So I really don't know what the parameters are, and you need to basically understand that if you want to optimize to that channel. You don't want to put all the money there, and then you really don't know so much about the parameter because you have a very flat signal. So yeah, that will be, you can definitely learn from it. You just need to be careful whenever you allocate to it.
Okay, thank you. The second one, do you have tips and tricks to help marketing managers embrace uncertainty? Many times they see uncertainty as a flaw or useless info, as they want to have a single value.
Yeah, that's definitely a very tough question. I think that if you have a marketing manager that is not right now speaking in terms of uncertainty, the best that you can do is just start to push them to understand that ignore it could actually result in worse outcomes. Again, in the first example, you will just guiding you by a simple single point. You didn't hit it, and you take a lot of decisions based on that, and you failed. So definitely, it's a tough thing, but I would say that the only way to do it is bring information and just have these conversations with them.
Thank you very much. There will be also a chance still to ask questions online, but now we do the round here. I see one hand. There are no more questions? Okay.
Yes, so for actual spend decision, right, you need to formulate the utility function. And at the end of the day, I suppose it's a CMO that makes the spend decision. So how do you get this utility function out of a CMO? Do you run a choice experiment and then analyze it with PyMC Marketing? Or how does that work in practice?
Yeah, that's, again, very good question. I would say that in real life, you definitely want to make the CMO tell you what will happen based on the outcome. So if they start to tell you, I have a lot of commitments that I'm planning to do, probably you will want to have utility functions that reflect that we need to be very certain, because we will take a lot of decisions on top of them. If the opposite happens, then probably you don't want to take, you can relax the amount of penalization that you want to put around the metric that you want to maximize or minimize. So yeah, I think making question to a CMO is basically the only way. You will never get a specific translation of, oh yeah, we should write this utility function. You will get some understanding on how much risk they can tolerate, and then your work as data scientists basically just translate that into a function. Yep.
Hi, thank you for the talk. My question is around, I see the model was always biased towards the data points that it already has, let's say, and in this case, when someone needs to go into exploration mode rather than exploitation mode, is there a way for the library to take that into account, or will it always deviate towards what has already worked before?
Yeah, definitely. I would say that that's basically the concept of you are not so much risk adverse, so you decide to spend even in places where you have ever spending before, and you can make experiments from it and understand, get new information, and then update the belief of your model. So again, as you get more data points in areas that you ever explored before, but now you're exploring, what will happen is, as I mentioned before, what we call epistemic uncertainty will shrink, because then you have more information to estimate the probability of the parameters given the data.
Questions? Okay, we still have 4 minutes. I'm checking online questions. There are none. So last chance. A big round of applause. Thank you very much.